Hey everybody. So this is a video that is building on the Kinetic Molecular Theory, KMT, simulation and worksheet that you should already have completed. You would have watched the PhET simulation, watching a bunch of those gas particle dots bouncing around in the container, and you would have attempted to figure out which of these statements are true regarding gases using that simulation. These statements that I have highlighted here are the statements that are in fact true. So the first one we've got here are gases are composed of a large number of particles that behave like hard spherical objects in a state of constant random motion. That is correct. The thing here that you want to kind of focus on is the constant and the random motion. So gas particles are constantly moving and they are moving randomly. So if you noticed, if you looked at any one dot, it was kind of doing its own thing and you couldn't necessarily predict what it was doing or where it was going. Which builds on to letter C. These particles move in straight lines until they collide with another particle or the walls of the container. So if you follow the dot around, it tends to move in a straight line until it hits something, and then it continues in a straight line after that point. D, these particles are much smaller than the distance between particles, so most of the volume of a gas is actually empty space. This is the one thing I'm not a huge fan of with the simulation, is it does not outline letter D very well. Simply because it would be really hard to see. And that's kind of the point of models and of simulations, is they are very rarely perfect. So just to kind of extrapolate on this idea more, a more accurate idea of what this simulation would have maybe looked like would be, this is the container, and then those would have been the gas particles. So when you imagine a balloon, for an example. So if you've got a balloon that's filled with gas, right? Most of the space that balloon is occupying is actually made up of empty space because the individual gas particles have so much distance in between them, and that distance between them is much larger than the actual size of the particle. So the reason that the balloon takes up space is because these particles are constantly randomly moving at very high speeds. So this constant motion maintains the shape of the balloon and maintains that volume as well. So that would be kind of a better depiction of what this would look like. Letter F, there's no attraction between gas particles or between the particles and walls of the container. This is true. So the gas particles move independently and freely of one another. So they aren't drawn to anything, and they're also not repelled by anything. They have complete free motion. H, collisions between gas particles or collisions with the walls of the container are perfectly elastic, meaning none of the energy of a gas particle is lost when it collides with another particle or with the walls of the container. This is true, and it's unique if you think about it. Like if I were to roll a ball right now, that ball would slowly lose energy as it was rolling due to the friction against the ground, or even if it was a frictionless surface, it would eventually hit the wall, and all of its movement energy, its kinetic energy, would go into the wall and the ball would stop. Or maybe it would bounce back a little bit, but it would eventually lose its energy. And gas particles are the opposite of that. So gas particles do not lose their energy when they hit anything. That's why they can constantly and randomly move. The temperature of a gas is measured by the average kinetic energy of the particles, or the average movement energy. That is true. So temperature is measured by how fast particles are. So like when you have a thermometer in your mouth and you're taking your temperature, what that temperature is actually measuring is the movement of particles. Faster particles have a higher temperature, and colder particles have a slower temperature. So that's what we're actually measuring there. So, kinetic molecular theory. These are the statements in regards to kinetic molecular theory. Breaking down this word really quick. Kinetic means movement. Molecular means molecules. Theory is an explanation for behavior. So this is basically particle movement explanations. So how and why particles move. A lot of these focused in on gases. And that's because gases are so unique when it comes to the three different types of states of matter. So you probably had a chance to play around with solids, liquids, and gases. And I would hope that you have noticed that gases acted a lot differently in comparison. So just to kind of go through some of these terms here. Solids move. So I want to be clear about that. That's kind of a misconception, is that solid particles actually have no movement. They do. It's a vibrational movement. So the particles stay in place, but they're vibrating in place. So like if you put your hand like on a surface right now that's solid, those particles are still in motion. They're just vibrating around one another. And the only point in which particles stop moving is absolute zero, which is measured as 0 Kelvin, and we'll talk more about that in this unit. Liquids also have movement, but they have vibrational and translational. So what that means is they can move around one another. They have a set volume still, so they're going to occupy the same amount of space, but they can kind of roll around one another. And then gases have complete free motion, vibrational, translational, free, crazy. They can do whatever they want, basically. Solids have a definite shape. So like this has a shape that doesn't change. This has a set volume, a set amount of space that it's taking up. Solids are very tightly packed. They're kind of condensed as much as possible. You can't diffuse anything through it. So like if I sprayed perfume on this remote, it would not travel through the remote. Compressibility, I can't compress this into a smaller volume. And these have the most order. So order basically kind of means like stability, if you want to think about it that way. So since solids have the most order, that means they're the most stable. Working through liquids, liquids do not have a definite shape. That's why you can like pour water into varying different glasses and it'll change its shape based on the shape of the glass, but it will have a fixed volume. Meaning if you've got 100 mils of water, it will maintain to be 100 mils regardless of the space you put it in. But its shape can change with those 100 mils. They're fairly tightly packed, not too crazily tightly packed. You can diffuse things through liquids. That's why like if you like drop food coloring into a liquid, it'll slowly diffuse throughout the liquid. That's due to that translational movement of the particles that kind of can bring other particles throughout the volume of the liquid. You can't compress a liquid, so you can't make it smaller than it already is. And it has some order, it's got some stability. And then gases, as you can kind of see, are completely off the charts. They don't have a fixed volume. They are not tightly packed. They do not have a definite shape. You can diffuse things through them. So like that's why if I spray perfume over here, somebody over there could smell it because it'll travel through. You can compress gases. So like if you've ever had gas in a syringe, you can make the volume of the gas smaller. And these have the least order, meaning these are the least stable out of the three. So if you kind of compare this chart here, gases are by far the most unique out of the three states of matter, which is why we basically have an entire unit dedicated to them. So this is your quick explanation on kinetic molecular theory, basically the explanation of particle movement. We're going to be using these concepts and these ideas throughout this unit. So the idea that gases have constant random motion. Here, I've got my spark notes right here. Boom. So gas particles are in random, constant motion and linear, so they're moving in straight lines. They're moving randomly, but their pathway is straight until they hit something else. Most of the volume of a gas is empty space. So like if you're looking at a balloon, most of that's empty space because the particles are small and there's a great distance between. Gases do have mass, so that's a misconception. So gases do have a mass. So even though they are mostly empty space, they do weigh something because it is matter. Gas particles have elastic collisions, meaning they don't lose any energy as they collide with things. And gases have the highest amount of kinetic energy out of the three different states of matter, basically meaning those are the particles that move the fastest. So we're going to basically be using these assumptions when we talk through gases. And one word I would like to introduce at this point is the word ideal. So all of these behaviors are ideal behaviors, meaning we assume they happen, they should happen, we'd like them to happen. Those are ideal conditions, but that doesn't mean it's always guaranteed. And that's something that we can kind of talk a little bit more about later too, when these behaviors deviate from the norm, from the ideal behavior, but these are all assumed ideal conditions.